understand the direct and indirect addressing and how it's set up by the operands. In higher level languages, the two values of a variable are known as its R value and its L value. In the assembly language used in this course, the level of addressing is controlled by square brackets. If you use the name of a variable without brackets, as in this example, the value copied into the register is the address of the variable. On the other hand, if you place brackets around the name, the value copied into the register is the value stored at that location, not its address. You can think of a variable with brackets around it as being a pointer. The result from the assembler is actually a completely different opcode, even though the same mnemonic is used. The assembler looks at the syntax of the operand to determine which actual opcode to generate. The same indirection thing is true of registers. In this example, the register name is enclosed in brackets, so the assembler knows to generate code that will put the value of 45 into the address stored in the EAX register. But there is a problem. There are different opcodes for different size operations, and the assembler looks at the registers used as sources and destinations to determine the size of the data item, and in this example, it can't tell. The location in memory could be a byte, a word, or a double. The assembler has no way of knowing. Now, to fix that, you can put a size specifier in front of the operands. That removes the ambiguity introduced by having the same mnemonic used for many different instructions. And don't forget, with a register address, you can always specify an offset. In this example, the address is calculated as being the sum of the number in the EAX register and the constant 10. Some notes on this size specification. First, the assembler does not calculate the size of any memory declaration. You can declare something as being a byte and address it as a word, or a double, or any other combination. To the assembler, the label is only a location in memory, and it can be any size. Second, it's perfectly all right to specify the size for any instruction, even if it's one for which the assembler can figure out the size. You can't change the size from what the assembler figures out. The size you specify must agree with the one that the assembler works out for itself. One thing I need to mention, I'm talking about the way the NASM assembler works. There are other assemblers that generate code for this same CPU, but their solution to this ambiguity of syntax is different. If you're accustomed to one of the others, you'll notice the differences. Personally, I think the NASM solution is the clearest and the easiest to use, but I thought you should be warned. There have been some other assemblers in the past that eliminated the ambiguities altogether, but they had other problems, and as far as I know, none of them have survived. The jump instruction branches from one location to another, and how they address their targets varies a bit. There are actually several variations to the opcodes and the way they store the addresses. This is one of those tedious jobs you normally don't have to worry about. The assembler figures out which one it should use. If a jump is very close, the opcode selected is one that can jump no further than 128 bytes forward or backward from the current location. This has the advantage that the target address can be stored in 1 byte. The next size up is the near jump. It takes 2 bytes of memory to hold the address, so the target can be up to 16K bytes away, forward or backward. The other type of branch instruction is the most rare. It holds the address in 4 bytes and can jump anywhere. It bears the name far because of the history of the chip. At one time, during the days of segmented addressing, a 32-bit address was called a far address. This course uses the C calling convention for its functions, which is to pass arguments by value. It's done by pushing the values of the variables onto the stack. The function can then use the values any way it wants because they will be discarded at the end of the function call anyway. One important note here is that clearing the stack after a function has been called is the responsibility of the caller. That is, if you push two 32-bit values on the stack to call a function, it's your job to pop those two 32-bit values off the stack when the function returns. The other option for passing arguments, and you can certainly do it if you wish, is to pass by reference. This is nothing more than pushing the address of the variables onto the stack. This way, if a function modifies a value, it is also modified in the calling routine. And it works the same way. It's up to the caller to clean the stack on return. Of course, this is assembly language, so you can use any method of calling you want. You can even make up your own, and you can even mix them in the same function. But that's probably not a very good idea. That sort of thing is hard to